All right, so this is our first section about equilibrium. Shh. So equilibrium is basically just saying everything is at equal. And specifically, we're going to be talking about forces. So let's look at our first example here. Did I give everyone a booklet? Or is there anyone who's bookletless? We're good? Okay. So we've got a 20 kilogram object being suspended by a rope as shown. We want to know what is the net force acting on this. So first let's look at the forces. What forces do I got on this object? I've got force of gravity, yep. And I've got tension. Now if this object is being suspended, unlike someone being suspended at school, suspended like this, what does that mean? Yes, but something more specific about this. What did you say? Equal forces. How do you know? It's not moving. If something is suspended, it means it's not moving. So these two forces are balanced. So what is my net force? Zero. Forces are balanced. Net force has to be zero. This is what we learned with Newton's laws. If there is an object at rest, will stay at rest unless you have an unbalanced force. No unbalanced force, no net force. So this is what we looked at last unit. How about this? Now let's take that same object and let's move it up at a velocity of 4.9 meters per second. What is the net force on this object? Well, we've got some force applied going up.
Oh, it's not tension.
Nope, it doesn't say anything about a rope.
But it says the same object.
Yeah, but it doesn't say it's attached by a rope. It just says the object's the same. Which of these two forces should be bigger?
Force applied.
Force applied? How so? Because it's going up? Just because something is moving up, does that mean one of the forces has to be bigger? No. There's a clue in this question. Okay, so because it's going upwards, the force applied needs to overcome gravity, therefore force applied needs to be bigger. That's really good reasoning, but this is not correct.
Because there is velocity, which means that not equal to zero.
No. If there's velocity, this does not mean that F net has to not equal zero. What's my velocity? 4.9. Is it constant?
No. Yes. Oh, it is?
It's being lifted at this velocity, which means my velocity is not changing, which means my acceleration equals what? Zero. And if acceleration equals zero, what does F net equal? Zero. So in this same case, F net equals 0 newtons, because I have a constant velocity. So these two forces are still equal. Even though I'm moving, my forces are still balanced. Remember when we talked about an ice skater that's gliding on the ice, and the ice is frictionless, and we looked at what are the forces that are acting on this. There's no force applied, there's no friction, so it even looks like this. And the argument is, can you tell from the free body diagram if an object is moving? So from this diagram, how can I tell this is moving? You can't tell, right? Whether it's stationary or whether it's in movement, the free body diagram doesn't always tell you that. And that's because the only thing free body diagrams tell you is if you have an acceleration or not. So if there's an unbalanced force, yes, it has to move. because you have acceleration. But if all the forces are balanced, I don't know if it's moving or not. You can't tell that.
There's an arrow that's pointing upward.
Yes, but that's not a part of the free body diagram. So that arrow just doesn't tell you anything. Not in this case. So what does it say? Because in both cases the net force in the object is 0, they are said to be in what we're talking about today, translational equilibrium. Stationary. Wait, I need to double check my notes on this. Because I don't want to mix you up on the different boxes. Sorry, this one's not translational equilibrium. This one's just equilibrium. You can talk about your project marks later. Right now we're in the middle of a lesson. So this is what we're going to be talking about. This unit is equilibrium. If the net force is 0, they're in equilibrium. If the object is stationary, this is what's called static equilibrium. So this makes sense. If something is not moving, it's static. So that's what static equilibrium means. Well, if we have an object like this one that's moving at a constant velocity, this one is what's called dynamic equilibrium. So some terminology here you're going to need to get familiar with. Again, think about static, dynamic. Dynamic, something's moving. Static, it's not. So these are both cases where we have an object that's in translational equilibrium. So I'm going to explain this in just a sec, but first I'm going to write it. So think about what it means to translate something. If you remember in pre-calculus, if we did a translation of a graph, that means we're moving it left, right, up, down. You're translating it. So translational equilibrium means it can move left, right, or up or down, but as long as it's not rotating, we're in translational equilibrium. So it can translate, but it's still in equilibrium, meaning all the net force is 0. And that's in general going to be what we're talking about is net force equals 0. Every single case that we're going to deal with in equilibrium, net force is 0. Yeah?
So equilibrium is basically when an object's net force is 0?
Yep.
That's the definition of it?
Yep. So all the forces are balanced. So those of you who are thinking of doing engineering, no matter what type of engineer you're planning to go into, you are most likely going to deal with this extensively in first year, at least from the programs that I've heard of. So this is your classic, you're going to build a bridge, you're going to build a building, you want to make sure all the forces are balanced because having something not move is typically ideal when you build a building, usually. There are crazy buildings in areas where they have lots of earthquakes that are designed to move with the earthquake, but that's a special case. So with translational equilibrium, there's a specific equation we're going to use for this. and then two sub-equations, but it's essentially the same thing. So for my translational equilibrium, this is referring to motion. So what we're going to have with this is we need the sum of the forces. So again, this is sigma. This is a capital sigma. This just means the sum of the forces is going to equal 0. So when I add every single force up, it's going to equal 0. And as we've seen in previous units, everything we've taken so far, we can treat different dimensions independently. So we saw in kinematics, we can treat x and y by itself. We saw in dynamics, we can treat parallel and perpendicular by itself. So same thing here. If I'm looking at the total forces 0, then the sum of all the forces in the x direction equals 0, and the sum of all the forces in the y direction equals 0. So these are two subsections along with that same equation. So we can deal with either everything all together in one go, or deal with the two components. So immediately in your head, you should be thinking trig method, component method. That's automatically what we're doing. So either I use this and use the component method, or sorry, this is components, this is trig. As you can see below, we have two strategies. So this is the equation you're going to use in order to solve problems. So here's a classic example. Something being suspended by ropes. This is a very common situation. So we're given this, and we want to know what is tension 1, what is tension 2. There's many different ways I can reframe this question, but this is essentially what I'm doing for this one. So we're going to solve this in two ways. First, I'm going to use component methods to do this. So we're going to follow the strategy that is on this piece of paper, and we're going to solve this. So the first thing I want to do, pick a point in the system that is in equilibrium, where all the forces are acting on that one point. So taking a look at our situation here, where is a point where all three forces are acting? Force of gravity and two tensions. The center. The point where all the lines intersect, right? So this is the point where all the forces act. We've got tension acting on this. We've got tension here acting on it. Yes, there's tension pulling down, but I'm going to oversimplify this. This tension is just equal to force of gravity. So I'm just going to say that's force of gravity. So choose a point that's where all the forces are. In this case, use let's just call this the center. Looking at this object, FG, tension, it's not moving. These are equal. So therefore here the tension going down is just equal to FG. All right, so that's the first thing. Next, any guesses what we're going to do next? Free body diagram. So let's draw this. We've got tension 2 is going up like this. We've got tension 1 is going like this. And we've got FG going down like this. Again, we're looking at what are all the forces acting on this single pivot point, because that is where all the forces are acting. If I add these all up, they equal 0. Yep. So for this, don't worry so much about the length of the arrows, because that's not going to be super important. So don't worry about that with drawing it out. So there we go. We've done 2 steps. Those are the easy ones. Next, break these forces into components. So let's do that. I'm going to redraw these arrows down here so I can break them up. So we've got T1. And again, it doesn't matter how I situate my triangle, if I do it like this, or if I do it up here. I'm going to do it this way. You'd get the same answer no matter what you did. For this, the reason I did it this way is so that I can see where the 35 degrees is. So if I compared this to this, my 35 degrees is up here. And then I can get what these are. Although, since I don't know T1, I'm just going to write T1x is going to equal T1, the hypotenuse, times, I'm adjacent to the 35, so this is going to be cos 35. And that's all I can do. I don't know what T1 is. So I leave it as this. T1y is this component. So again, I don't know the hypotenuse, so I'll just write it as T1. And this time it's sine 35, because it's the opposite side of 35. Good with that so far? No, because I'm not dividing those. So I can't cancel out T1. So I just leave it as it is right now. Because I'm not dealing with mg. I'm just breaking up T1 into components. So I haven't touched FG yet. So next, let's do T2. So there's T2. Again, I'm strategically picking how to draw the triangle so it fits with this angle I have up here. So I'm going to draw it out like this, so that my 50 degrees is up at the top. So there's my triangle. Then, again, we're going to just split this up. So here's T2x up at the top. This is equal to the hypotenuse, T2. It's cos because it's on the same side, or it's adjacent to the 50 degrees. So there it's cos. And if I do T2y, here it's T2 sine 50. Sorry, it's slanted. And then, thankfully, FG is already in its components. It's simply the y direction. We have no x component for gravity. This one just stays the same. So FG, this one I know what it is. It's, are we given the, yeah, we're given that it's a 64 Newton object. So we have this. We don't need to touch FG. Any questions with breaking this up into components? You've seen this since the very beginning. Yeah?
Why are we ignoring that? Why are we not ignoring that either?
Because I want to look at the single point where all the force is acting. So that's why I'm not drawing the FG down here. I'm doing it at that single point. So with translational equilibrium and all of this section, we look for that single point where all the forces act. So yes, at this point there's tension pulling down, but that tension is just equal to Fg that's down here. Next, well, the last step is we're going to use these general force equations. So use the sum of Fx equals 0 and the sum of Fy equals 0. From this, we can solve this. There'll be a little bit of algebra in the middle, but using this strategy, we'll get our results. So with this, we're going to need to use a lot of substitution this unit. So that's going to happen fairly regularly. Because as we write this out, so if f of x equals 0, that means all the x forces going to the left equal the x forces to the right. Correct? Does that make sense? If all the forces equal 0, the ones this way must equal the ones going this way. So that means, I'll write it out explicitly for the first time. For all the other ones, I'm not. So the sum of the forces in the x direction equals 0, which is equal to forces to the right. So T2 cos 50 minus forces to the left, which is T1 cos 35. Just x direction. So from this, because they equal 0, that must mean that T1 cos 35 is equal to T2 cos 50. Algebra. I'm going to leave it at that for now. Let's look at the y components. I'm not going to write it out as explicitly this time because it's just a big equation. Forces up have to equal forces down. That's what the sum of the y direction equals 0 means. So this means my Fg, the force down, must equal the forces up. So T1 sine 35, this is my y component going up here, plus this y component here. Come on. That's sine 50, in case you can't read it. So again, forces up equal forces down. So these are my two equations. The problem is, two equations, two unknown values. So this is where substitution comes into play. So what you're going to need to do is solve for either T1 or T2. It doesn't matter which one you solve for. Solve for it in one of the equations, plug it into the other. You're going to use this strategy many times over. So in this case, it's just easier to do this one. So it doesn't matter. Let's just solve for T1. T1 equals T2 cos 50 over cos 35. Please do not just cancel out the cosines. I'll be really disappointed if I ever see that. But it has happened. I'll get to it in a sec. So once I have done this, I'm going to substitute this into here. When I do that, I will now only have a single variable. Right? If T1 equals this, anywhere I have T1, I can replace it with that. So I will get this equation. I need a little bit more space. Let's do it down here. So Fg equals T1, which is just this. T2 cos 50 over cos 35 times, because don't forget T1 times sine 35 plus T2 sine 50. By now, I sure hope you're comfortable with something like this. This should not freak you out by now. Why? Cos 50 is a number, cos 35 is a number, sine 35 is a number, sine 50 is just a number. That's all those are. So now I can actually go about and solve this. I'm not going to, at this point I would say just use a calculator to plug these numbers in. And here's why, because I'm going to make your life a whole lot easier by doing this. So FG, this is 64. Let's go cos 50 divided by cos 35 times sine 35. That's a 4. Does that make you less hesitant with this? That's T2. So if I've got a number of T2s plus another number of T2s, add the two numbers together and I've got that many T2s. If this was 4 T2 plus 2 T2, just 6 T2. So all I'm doing is just adding those two numbers together. So 0.45008 plus 0.76604 gives me 1.21612 times T2. Now you solve for T2. Yep, and I said I would get to your question in just a sec. Let me finish this off. So T2 is 52.6 newtons. So that's from going and doing all this. You're going to end up with equations with lots of sines, cosines, whatever. If it makes you more comfortable, switch it into numbers. Just be very careful when you do that with rounding. Because if I try and do this without rounding, let's see, cos 50 divided by cos 35 times sine 35 plus sine 50. So if I did this without any rounding, oh, it gets me still somewhat similar. 52.625. So it would still be the same. But rounding can make a difference. Thankfully not in this one. So just do it like this. Just be very, very careful with the rounding of numbers. Try not to. The best is to round at the very end. So for instance here, I've got this number is rounded, this number is rounded, but in your calculator, try and use the answer button to use the exact numbers. Am I done?
Plug the T2 back into the equation and solve for T1.
You were asked to solve for T1 and T2. I've only solved for T2. I need to solve the other. But this is the easy part. I have T2 times cos 50 divided by cos 35. Easy. So just plug that back in. 52.6 times cos 50 over cos 35. What does that give us? Times cos 50 divided cos 35. 41.3. So notice with this, I do not care about direction in this unit because all the directions are given in the question. So you really don't need to worry about direction with your answers. Just give me the magnitudes and you should be good. All right, you got a small question.
First point,
Yeah, so this, it doesn't matter. If I switch these, it'd still be the same thing. So it doesn't matter that I did t to x first and then t to x, or no. Because if I switch these, it just means when I rearrange it, I'm putting the other one on the other side. But it's still the same.
But doesn't that really follow our equation of like
So they do. So the sum of the forces do equal 0. Because we said here, the forces to the left equal forces to the right. And we technically did the same thing here. The up force, or sorry, I said the down force equals the two up forces. Because they have to balance out. So I skipped the step saying sum of Fy equals 0. Because if I put it here, it just would take up space. But this is saying that the y components of the forces are all balanced.
so the final answer of tension and force of gravity does not equal 0? Like,
You're saying like the individual forces have to equal 0? Yeah, so the individual forces in the components will not equal 0. But if I now did my T2, so if I did 52.6 times sine 50 plus whatever this one was, 41.3 times sine 35, if I added those two y components together, they would equal 64. And if I did T2 cos 50 and T1 cos 35, they would equal each other. They're just in the opposite directions. So it would work.
that means we're going to use the T1, then at the end we're going to get T2?
You mean at this point, if I solve for this one instead? Yeah. So if I divided by cos 50, I would solve for T1 on this side and then solve for T2 here. Yeah. So it doesn't matter which number you substitute, you're just solving for the opposite one.
Then I feel like during the whole unit, we won't care about direction.
Which
one is bigger?
Just trying to think. In later sections, the direction you won't, how do I phrase this? There will be some questions where the direction is important, but that's more for forces that are not shown in the diagram. So for instance, here, you have the angles. So you know what direction those are pulling. There's going to be other cases where that's not going to be the case. But I'll show you where that is, because I do it in the notes. Gustav, is your attention span really that short? So because you can't wait for 2 minutes for me to answer a question, you have to be on your phone right away? Okay, so this is the other strategy. In general, I typically more work on the component method that we just did. I find that one's in general easier. However, you can still solve this using the closed vector diagram, which is just simply the trig method. And you'll find in some cases that this is very easy. It's actually way easier to do this one. However, I just like the component method more. So since we know that F net equals 0 at any point in equilibrium, if we add all of the forces together, it's going to equal 0. Net force equals 0. Therefore, when I add all the forces up, my resultant should be 0, which in turn gives me a closed vector diagram. So I'll show you what this means with the last example. So we had something like this. So I had T1 look like this. T2 looked like this. And here's FG. So notice I get a closed triangle when I draw this all out. This is what I mean by a closed vector diagram. When I add all the forces up, it equals 0. Because notice I started here T1, T2 plus FG gets me back to the original position. This is what it means by an closed vector diagram. And with this, notice, again, just the results into 0, which means all the forces added up equals 0. Yeah. So in solving this, we can set up our diagram like this, and we're going to use either sine law or cosine law, or sum of all the forces equals 180, all these kind of rules in order to solve this. So in this, use another order means to solve the triangle. That should be a period. Nothing else to say with that. And one thing that you need to make sure of with this is never assume it's a 90-degree angle, unless you can prove it. So for instance, in mine, it might look like over here it's a 90 degrees. Just based on what I drew, don't assume. Never assume it's 90 degrees until you actually measure it. So let's try this. So based on the diagram from the first page, we know this is 50 degrees. We know this is 35 degrees. And we know FG over here, this is 64. And we're looking for T1 and T2. Thinking all the way back to trig method, what was the first thing we needed to try and do with something like this? Z rule would definitely help us for this. How would the Z rule help? So is this whole thing here 50 degrees? Or is the whole angle 50 degrees? The red part or the combination? Just the red part. Why is it just the red part? The Z rule, two parallel lines and the intersecting line. So my two parallel lines are between the horizontal, this line, horizontal. Not between horizontal and some angle. So it needs to be between two horizontals or between two verticals. So this is great. This helps me immensely because now I know what this whole angle is. And with one whole angle in the triangle, I can do a lot of things. So that means this whole angle here is 85 degrees. What else is special that you can tell me about the angles in this case? You can get this? How do you get this? Perfect. So, something special we know about FG. It's vertical. It's not at an angle. This one's completely vertical. So therefore, that tells me a bunch of things. That tells me that from horizontal to vertical is 90 degrees. So therefore, this must be 90 minus 50. Right angle is 90, minus part of it, you get the rest. So this has to be 40. Triangles. That's what happened. FG is vertical. The dotted line is horizontal. Intersect those two, you get 90 degrees. You're given that this part is 50, so the rest of it must be 90 minus 50. Unless you can prove it geometrically, which I just did. The dotted line I said has to be horizontal, and FG is always completely vertical. So geometrically that does work. Then, well, do we need the, yeah, sure, why not? Let's figure out what this angle is. It'll help us later on. So how could I get this angle? Well, let's take this horizontal line here and extend it. Because this is horizontal, this is vertical. What does that tell me about this angle and this angle? 90 degrees.
But why can't we just do 180 minus 40 minus 85?
Oh, that works too. That works too. Well, yep. You get the same thing. So this one's just, I've either got this little triangle, 180 minus 90 minus 35, or the big triangle, 180 minus 85 minus 40. Either way, you get the same thing. So 555. He was supposed to be going to the bathroom. I'm double checking. Yep, good. Does this 90 degrees make sense?
Yes.
So right triangle. Yes? 180 minus 90 minus 35 gives you 55. Or as Habiba brilliantly pointed out, in the whole triangle, I have two angles already. I have this whole angle is 85. I have this angle here is 40. Therefore, this has to be the rest of it. Either way works. Triangles are a beautiful thing if you know how to use them. With this, I can solve for everything I need. Yeah, so either use sine or cosine law, it really doesn't matter. I think it's much easier to use sine law in this case, but there's some cosine law fanatics out there who want to do that, so be it. So let's go T2. So T2 over sine of the opposite angle. So here's my T2, opposite angle is 55, equals, we need to pick the pairing that we have both, which is FG and 85 degrees. So this is equal to FG, which is 64, over sine 85. And then solve for T2. Actually, I'm going to extend this a little bit. I'll put FG so you can see what it is, at least for on the video. So this is 64 times sine 55 over sine 85 number. Do the same thing for T2. I can use the same opposite pairing. So T1 over the opposite of T1 is 40. So sine 40 equals, we could do the same thing, FG over sine 85. By now you should know where to go with that. Times by sine 40, bring it up here. So T1 equals FG, which is 64 sine 40 over sine 85. Yep. Yeah, it doesn't matter what order if you do times first or divide first, doesn't matter. So in this, make sure your calculator is in degree modes. This will cause many an error if you do not do that. But from this, you should be able to do that. No problem. Yep. That's the sine law. This comes from the sine law. I assume you should know the sine law. A over sine A, oops. This should be lowercase, I think. So there's this. You can also use the cosine law. It's on the formula sheet. Can you use the notes for your test? No. If you use the formula sheet that I gave, it's on there. Cosine? Yeah. That works too. If you want to solve for the opposite side, c squared equals a squared plus b squared, so you'd have to figure out one of the other sides first. Minus 2ab cos c. So yes, that also works. Let's do one more example. If you want to just work quietly instead of pay attention, you're more than welcome to. Yeah. But I'm going to show this one. So if you want to work, you can start working. No. So what you're going to do with this one is follow the same strategy. I'm going to use the component method. If you want to use trig, more than welcome to, but I'll use component. So I'm going to do this quickly, no questions asked until the very end, so I can finish this all off in one go. So you can see the whole process, start to finish, no interruptions, hopefully. So looking at this first, I'm going to discover where's the point where everything meets. And very often it's going to be the point where all the lines intersect, which is going to make it pretty easy. So from here, my forces, I've got T1 pointing this way, T2 is pointing this way, FG pointing this way, or weight, because sometimes they tell you the weight. And then I need to, even before I read the question, I just do this automatically. So an object is suspended, so it's at rest. If the tension in one of the ropes is 50, so we're told that, what is the weight of the object? So what is FG? Notice I don't even care about T1. But what I can do with this, let's just split this up. So I've got T2y is here, T2x is here, and from this I know this is 37. Just by looking at my angle here and extending it into the triangle. So that is my diagram. If I want to know the weight, so weight is just Fg, same thing. I know that this, the weight, that's the only down force. This must equal the only y force going upwards. So this is equal to T2y. In looking at my diagram, T2y is the hypotenuse, T2, times sine 37, because it's on the opposite side. And wonderfully, we have all this information, so it's 50 sine 37. Plug that in your calculator, you're done. Just like that. So really easy. Get some number. I'm not going to plug it in. If I asked you for T1, it's like this question's done. This is it. That gets you your answer. But if suppose I asked you for T1 as well, I just look at the x's. So T1, that's purely in the x direction. This is equal to the other force pointing to the right, T2x. Again, I can write this out as T2 cos 37, looking at this right triangle. And there you go. That one's really easy. So just because it's a tension question like this or equilibrium doesn't mean it's hard. You just need to know the strategy. So notice here, component method, much easier. Technically, if you did trig, it'd be something similar, but it would take you about the same amount of work as up here. So here, this one's better. So just as a hint with stuff, as I said in previous sections, you don't need to use both methods on the test. However, it's great to know both strategies. Just in case. Because sometimes you might get stuck using one method or the other. So for instance, on your the dynamics test where you had the grid with all the different forces, and I asked you to add what, like 4 forces together? Using the component method or the trig method would have been a terrible idea. Because you would have had to add 2 of those forces, then take the resultant of that, add the third, then add the resultant of that and add the fourth. would have taken you the whole test just to do one question. Whereas components, take all the x components, add them, take all the y components, add them. So if you would have come to this set of notes or the other one saying, I'm only going to use the trig method and not study the other, you wouldn't have been able to do that question very easily. So just be aware of that. It's good to know both. In general, the component method is a fairly easy method to go through. All right, I'm going to stop it there.